we're going to introduce ourselves. I hope everyone can hear us okay. I'm Monika Kreitmair, and this is Nick Makasis. Or I'll do both. So we work with Ruchi Chowdhury as part of the Energy Efficient Cities Initiative, which is part of the CSIC, and also the Data-Centric Engineering Group at the Alan Turing Institute. And so we will be speaking a bit about our work today on underground climate change modeling or underground thermal modeling. I will start by, sorry.
Yeah, maybe we can
I'll start by sharing, we'll go straight into the presentation. We'll share our screen. Can you see? Ah, yeah. So hopefully you'll be seeing our screen, the presentation now, I believe. Yes. So, right, as I said, things I was going to say on the slide, I have already said. So to give a bit more of a project overview, this is a international collaboration between entities and research institutions in the US, in Australia, in Germany, and also here in the UK. And it's about understanding better what the thermal impact of human infrastructure within the shallow subsurface is on the surrounding ground. And this is done really, if I go make this a pointer, a later pointer, this is done really through a combination of modeling and also deploying monitoring instrumentation into the ground to collect data to supplement the numerical models in order to capture a thermal map, as it were, underneath cities or underneath densely populated urban centers, and to identify planning and mitigation strategies for a more sustainable use of the ground as a resource. And really, one of the final outcomes we want for this is a modeling framework that allows a efficient modeling and efficient generation of thermal maps underneath cities, really anywhere in the world on a global scale. And so perhaps to kind of indicate how much really this makes a difference, how much really the anthropogenic heat flux into the ground can have an impact, and perhaps relatably we can look at the London Underground, where 100 years ago it was actually, as shown here by this marketing poster of the London Underground, it was actually somewhere you would go if it was very hot outside up on the surface, because it was, a very temperate 14 degrees Celsius at the time. Whereas now we're in a situation where frequently and regularly you record temperatures in the high 30s, low 40s in the summertime of the London Underground on various lines. And the reason for this is that the London clay around that the tunnels are built into have really accumulated all this heat and are no longer able to transport away the heat and really impact the thermal comfort, quite noticeably so, the thermal comfort of passengers underground. And really this is a problem, as I said, for this thermal comfort and this ventilation cost issue. Again, if we think about the London Underground, one of the issues is that there isn't enough space between the tunnels and the trains to employ air conditioning. So it really is becoming a bit of a question how to take care of this or how to mitigate this. It also impacts groundwater temperatures and the health of ecosystems reliant on groundwater. And it also impacts the productivity of goods produced underground, such as underground farms, for example, growing underground, and perhaps equally importantly, also the quality of wine stored in wine cellars. But there's also some opportunities for this. By having more heat injected into the ground in higher temperatures, we have a situation where you also can harvest more heat and on a local level you have more efficient heating of houses nearby from ground source heat pumps. But also, if we acknowledge that the ground is this shared resource and a continuum, and what heat you inject at point A impacts the temperatures further afield at a point B, we need to start thinking about this at a city scale, a more large scale even, such as, for example, here in this study by Thyssen et al. For the city of Vienna in Austria, where they're trying to identify the best locations for heat pumps. We need to take into account the thermal interaction between heat sources and sinks in the ground in order to plan and develop these more efficiently. And so really that's where we're wanting to go. We want to, at a city scale, we want to develop a thermal map accounting for, underneath the city, accounting for the various heat sources and sinks within that city. And we're doing so, as implied earlier, through two aspects in our work, one being the numerical modeling side and the other being the data side that tethers the numerical model to the real world. I'm going to hand over to Nick, who will be speaking about the numerical modeling aspect of things.
Thank you. So first, let me introduce you to the city of Cardiff, which, as the title suggests, we have used as a case study for the work we're presenting today. And the reason is that our partners at the British Geological Survey have a lot of high quality and high quantity of data throughout the city. And this is the city center that is shown here. So there's a number of monitoring boreholes that record temperatures at different depths over time. And here we can see kind of a snapshot of what the data look like. This is at different depths. And you can see there's a range of different temperatures and temperature variations depending on the location and the depth. And therefore the data itself have an interesting story to tell. Cardiff is also, so it's a relatively simpler case compared to other more bigger and more complex cities in terms of the subsurface. For example, there is no metro system. So the main anthropogenic heat source are the basements. So the basements of the buildings, which can be heated and then have anthropogenic heat flux into the ground. And then also finally, again, through BGS, we have detailed geological data for the area. We know roughly we have layers of made ground. At the top, we have aquifer being of glacial fluvial sediment deposits, and then the bedrock is Messian mudstone. So the modeling framework has been developed within our research group, and it is a semi-3D approach in that we're using a collection of 2D planes that are coupled between themselves. And this approach, the fact that this is not a full 3D model, and it's simpler and has lower computational costs, thus allowing us to model larger areas, district scale or city scale. So what our modeling is, we're modeling the thermal and hydro processes. Within the planes, we are modeling heat transfer equations in terms of conduction and convection, as well as Darcy's law for the fluid flow. And then we are the planes are coupled in terms of the heat fluxes interplanarly in terms of conduction. So with the model, what we want to do is go below the surface as indicated, and we want to look at how the subsurface looks like, how the temperatures of the ground can be affected, what kind of propagation we can have, and how these can accumulate and change over time with the different interactions. So we can look at different scales, starting from the left here. We can look at surfaces. This is at 5 meters below the ground. We can see how when we have flow, the thermal plumes are affected, and how the temperatures between the different interactive elements develop. Similarly, we can look at slices and again, how deep temperatures propagate, which both are looking at this on a more holistic level, or we can even go to the individual point and look at a specific location what the temperature is, both with depth and time. And this, of course, resembles the data we get from boreholes, which we can then use to validate the model, which we've done for Cardiff, to make sure that we have confidence in the results. So having a developed model, we can then go a step further and try and find a good balance between accurate results, but also low computational costs. Because when we're talking about modeling city scale, we need those computational costs to be as low as possible, and therefore we need the model to be as simple as possible while still providing accurate resolution for the results. So what we have done for this case, we've looked at three main ways that we can potentially simplify the model. And the first one is the elevation of the ground. So how much in detail does this need to be modeled? And we have a realistic case here at the top that takes into account the different elevations throughout the area, and also a simplified case here at the bottom. The second parameter of simplification has to do with the groundwater and the hydraulic head. You can see here that in Cardiff, the groundwater is controlled. So we have these interesting points of control. And this is the realistic one, and we've simplified it to be more of a linear distribution. And then finally, we have the basement footprints. So this is on the top is how the basement footprints look like and building footprints look like. And I mean, in reality, we can have quite complicated shapes for this, which when we're talking about finite elements and meshing, this can result in quite complex meshes, which can be potentially unnecessary. So what we have done here to check this is we have introduced the basements in more simplified shapes while keeping the placement and the total area consistent. So for each of these different combinations of models we've run for either of these being either realistic or simplified. So here we're looking at some of the results. We have the plot shows the volumetric temperature from the surface and how this develops over depth. And we have two sets of lines. On the left-hand side, this label unheated here is all the models for which the basements, the main anthropogenic heat source, is the basements are unheated. So there's essentially minimal anthropogenic influence into the ground. And then on the right-hand side, we have the results for when we do heat the basements. And in this case, it's up to about 18 degrees. And what we see here is that we have a difference in the, again, volumetric temperature. So in the temperature of the ground of up to about 1 degree, about between 20 and 30 meters, depending on the simplification, which can be significant. And to illustrate this, we've translated these results into a more practical application. So in this figure over here, we are showing the difference for each of these cases, the difference between having the basements heated or unheated, how that difference translates in the application of designing a typical ground source heat pump system. So essentially what these results show is that if we do account for the heat that the basements transfer into the ground, we could potentially either provide about 9% more shallow geothermal energy, or equivalently, we could design a system with lower capital costs, in this case about £1,800 less. And then on a second note, we can look at the simplifications themselves. So look at the difference within this cluster of lines. And if we look at the zoomed version here, we can see that when applying the different simplifications, either realistic or simplified for all of these metrics, we have a difference of about 0.3 degrees in terms of the absolutes. And what this translates is difference here in terms of the energy gained, which is about up to 2% in this case. The biggest difference comes from modeling the basements, which, for example, it's the difference between these two or every second pair. While the modeling of the elevation and the hydraulics for this case were shown to be much less impactful. But again, it depends always on the context. In this case, we can say that either of these simplifications could have been used to get reasonable results and have confidence with lower computational costs. So passing on to move to talk about the data.
Yeah. So having a model that runs relatively efficiently, but still provides results that are accurate within a threshold, depending on the application, we now want to connect it to the real world using data and calibrating these models and determining parameter values. So going back to the data, which we have for the domain within the Cardiff city centre, we have again for these 24 points, we have as time series temperature data that constitute the field observations, and we have a numerical model which outputs data, similar data, and we want to find the parameter values that are inputted into the model that best match the field observations. And we do this using a Bayesian calibration method based within a multi-fidelity framework, where we have a low fidelity model and a high fidelity model. And the low fidelity model can be run at a much lower computational cost, but you can generate significantly more data with which you can then run calibrations, but at a lower accuracy, but you combine it with the high fidelity model data to provide more accurate points. And these are then statistically compared to the field observations for a particular state of the points, i.e. the locations, in order to find the most influential model parameters. And the values for the model parameters is what we are going to be focusing on next. So looking at some of the results we get from applying this calibration method, we needed to find the most influential parameters. So the parameters that the model output is most sensitive to. So we were focusing on the mean temperature at those 24 locations. And we found that those are the far field ground temperature, the hydraulic conductivity within the aquifer, and the basement temperature, so the temperature of the heat sources, of the anthropogenic heat sources in the ground. And so running the calibration, we obtained these posterior distributions for those parameters. And in all cases, the calibration was able to constrain the uncertainty that we had from our prior beliefs, represented here by the black bell-shaped Gaussian distribution, and really constrain the values for the parameters. Something that we looked into was the option, or was our ability to feed in further information to the calibration via the state variables. So we have the solid colored lines and so the state variables are the variables that identify the point, the measurement location, and the solid color lines are results from the calibration performed using the standard state variable formulation, as we call it. So using only the XYZ location, and then the dashed lines show the parameter distribution inferred by calibrating on what we call extended state variables, where we are able to further introduce or further distinguish the data points by virtue of physical phenomena taking place. So in this case, we added whether or not a point is located within the aquifer or not, and its distance to the nearest heated basement. And we find that this gave us tighter or more constrained uncertainties and tighter values, particularly for the hydraulic conductivity. And we also found that the values we get seem to be more in line with what we would expect For example, for the far field ground temperature, we see that the new, albeit small change, but that the new mean of the mean that we get from the calibration using extended stage variables is 12.9, which matches exactly the temperatures we find with very deep borehole measurements within this area. Also, something we looked at was how the calibration, or how the information that the calibration can infer about the parameters changes with the size of data points. Because getting data on the subsurface is expensive, we want to be able to calibrate using the minimum number of points in order to drill the fewest number of holes in the ground. And so this in particular depends on the information that is contained within each point. And we can see these qualitative changes in the posterior distributions. These are the colored distributions upon changes in the subset size or inclusion of more points. And this is something that we're working more on in the future, where we want to be able to identify exactly the crucial measurement locations within a domain to inform our models in order to minimize costs of data acquisition, and also to equivalently really be able to say from 2 points, maybe of 2 points, if they have the same information or they provide the same information to the calibration, that one of them can be neglected. And finally, something that we were interested in is to see how our outputs of the calibration translate into the real world. And in particular, or fortunately enough, we actually have a installed open loop system within the domain we were modeling, namely the Grangetown Nursery School open loop system. So there's an injection and a production well just at this site. And originally the system was designed with lacking detailed information about the subsurface, and it was designed for about 22 kilowatts of energy. But using the distribution of the hydraulic conductivity that we found in the previous 2 slides ago, which is an important parameter in the designing of open loop systems, we find that the system could provide at least 38 kilowatts of peak load for the current spacing of 20 meters between the production and the injection well. And we also see that if we completely ignored any spacing constraints, we can get much higher, or we can get much higher maximum theoretical peak loads. And so it shows that it's important to account for uncertainty in the design of some of these systems in order to make more efficient designs. So finally, just a quick mention about what we're aiming to do in future. As we said earlier, what we're really interested in is this sort of city scale thermal map of the underground. And what we've been doing so far is at the district scale, trying to understand modeling and uncertainty considerations that are important for mapping of the thermal mapping of the underground. And what we want to do next is to move on to a much larger scale, where we can go from the input we have for the data input we have for a location over to a thermal underground map, which we're also able to use to forecast future scenarios and therefore better plan the construction of infrastructure in the ground. And we are proposing an archetype-based framework for this, which first divides the city up into smaller blocks of predefined volume, and then identifies each of these blocks as being part of particular archetypes, a finite set of archetypes that we have identified, and for which we have trained emulators that connect the input from a block to the desired output of the temperature, and then recombine those to generate the city scale output. So this is work in progress. And the benefit of this, the quick computational aspect of this, will allow to produce various scenarios, future casting scenarios. And that is all from us. Thank you for your attention. And we're happy to answer any questions.